Hi, in this video, we'll now talk about what happens to singular points and in the context of the Euler equations. So in the previous video, we already said what is a singular point. It is a point where it causes the capital P to be 0, or it is the point where small p and q is the denominator is 0, or the points where this functions unanalytic. So a relatively simple ODE will be known as the Euler equation if it's of the form x squared y second derivative plus ax y prime plus beta y. We'll see why we want this type of equations later on, and we'll be able to solve it actually. So in this case, we know that x equals to 0 is the only singular point, and so for convenience sake, we'll first consider the interval x larger than 0, then consider x less than 0. So we want the solution to this we know it's a singular point, so we don't know, we can't say that there will be a series solution, and we must now think of a way to get a solution. So what we recognize is that if once you differentiate once, you get x r minus 1. But then here is x times y prime. So it actually becomes xr again. Here is xr. Here will be xr minus 2. Then you times the x squared. So it's also xr. So this is very useful. So this allows us to pull out the xr. And here is a quadratic equation we get in terms of r. And now we want this equation to equal to 0, which means that since this part we can't equals to 0, this portion over here must equals to 0. And so we solve for it, and R1 is of and R2 are of these solutions. So this is the same idea as when we were to do it with constant coefficients, and then we want to remove the ex. So in this case now, because it's not constant coefficients, we have the x squared x and a constant here. We use the monomial x to power r, and we actually see that we get this quadratic equation which allows us to solve for the root of r. So if they are distinct, real and distinct, then of course the solution will be x to power r1 and x to power r2. And we actually can check that the Weinskian don't give us a 0. So this tells us that y must equals to a linear combination of this fundamental set of solution. Next, so we see an example to understand it better. We have this Euler's equation. Substitute y equals to r x to power r, solve for the r, and we get this y equals to c1 x to power half plus c2 x to power minus 1. But remember, in every case now, we are looking at when x is larger than 0 only. We'll talk more about the x less than 0 part later on. We'll first see how the solution plays out. So when they are equal roots, then we again only obtain one solution, but we know it's a second order ODE, so we need a second solution, and we can just use the method of reduction of order to help us. But we will now introduce an alternative method, and it is that this quadratic equation must equals to 0 at r1, and the prime of it must also equals to 0, because if you take the prime of this is 2r minus r1, and so when f prime r1 is also 0, we can use this as a second equation to help us solve for another solution. So what does this mean is that we just need to differentiate this equation once more, and then set R equals to R1. So we actually get that x to the power r ln x equals to 0 is will cause the differential equation to be solved. So another solution is actually x to the power r1 ln x. And if we evaluate the Wronskian of these two solutions, we actually see that it is non-zero. Hence, the fundamental set of solution is x to the power r1 and x to the power r1 ln x. Next, we have the complex roots, and again, the idea is like the same as when you have constant coefficients and you have complex roots. What you want is you want to write your x to the power lambda plus I mu as of the form with the trigonomic term, which is like this. By doing so, now we see that we can simplify it and obtain the real value solutions, x lambda cosine this and x lambda sine this. And we find the Wronskian to see that it's non-zero again. So this forms the fundamental set of solution. Hence the general solution will be C1 x lambda cosine mu ln x plus C2 x lambda sine mu ln x. And we see an example to help us verify our understanding. Our r is plus minus I, so the solution will be just C1 cosine ln x plus C2 sine ln x. Because plus minus I here is 0, so it's 1. Then the sine is sine 1 times ln x, so it's sine ln x. Now our idea is we want to extend the solutions to when x is less than 0 as well. Because when we use the monomial x power r, if x is larger than 0, then there is no problem. But now the question is, what happens when x is less than 0? You see, when x is less than 0 and r is maybe 3, then it is sometimes positive, sometimes negative. So it's kind of weird. And what's more, if it's like x to the power of half, then it's imaginary for x less than 0. So is it possible to obtain a real value solution? The answer is yes. And we'll just need to make a following change, which is let x equals to minus epsilon. Then epsilon must be larger than 0 because x is less than 0. Then we let y equals to some function of epsilon. And with the chain rule, we're able to simplify our equation to change it from a differential equation in terms of x to a differential equation in terms of epsilon. And after that, we solve for this because we know epsilon is larger than 0 using the normal way. And then once we have this, we replace epsilon by minus x. And we're done. And we actually see that once you replace epsilon with minus x, you actually arrive back to the same equation form. You see, same type of equation. So we can combine the results to just use the modulus notation. So if the roots are real and distinct, then you just have this form but with modulus x. If they're equal, you have this but with modulus x. So if you have any question about this, please leave it in the comment section. Else you should be able to see how it plays out. So in general, if your solution equation is of the form this, not center at 0 anymore, then your singular point is x naught. Then we just need to make the corresponding translation to the solution, and thus it will be of the following form. You have your modulus, but now instead of x, you have x minus x naught. So I hope it's not too hard to understand that for the x less than 0 case, it's exactly the same thing. And now you want to combine the two solutions set into one. You just need to say x. You just need to use the modulus. And for the general solution in a general Euler equation, then you just need to translate the solution to the singular point. And so what is the difference between the regular and the singular point is what is a regular singular point and what is an irregular singular point is that what we want is a singular point if the limits of this and this are both finite, then x naught is a regular singular point. Otherwise, it is an irregular singular point. In this aspect, it will motivate our idea into finding a series solution. So, some examples of what is a regular or irregular one is, let's say we got this. We want to find the singular points, which is just x equals to 1 and minus 1. Then we just find the limits, or we just check whether the limits hold. So we take the limit of x minus x naught times qx over px. And then we see that the limit is equals to 1. And for the other case, we also do the same. We show that the limit is 0. And so, because both limits exist and are finite, then x equals to 1 is a regular singular point. And in a similar manner, we will be able to show that x equals to minus 1 is also a regular point. And that will be left for you to do. So, another example for irregular one is you have this differential equation. Then we see that x equals to 2 and x equals to 0 are the singular points. For x equals to 0, the limits exist, so it's regular. But for x equals to 2, we see that the limit does not exist. Hence, x equals to 2 is an irregular singular point. So this is just a definition of regular and irregular singular point. It will motivate our example later on to finding a series solution for this Euler's equation. And that's all for this video. I hope you have enjoyed it. I hope you have understood how you find the solutions for an Euler equation using y equals to x power r and modifying it later on to actually form this general case. That's all for this video. Please like, share and subscribe, and I'll see you again. Hit the thumbs up button if you can. Bye.